remarks I really like. As soon as you invent something really striking and people find it's obvious, they think, well, it's nothing, but as long as you don't know about it, well, you don't know it. And in this line, in a way, we will have the next presentation soon. And we have mathematicians and computer scientists here. And in a way, there is a big overlap between these disciplines. And there are also shared topics between the disciplines, but there is a big, big difference between those two between these two disciplines. Mathematics is a very, very, very old discipline. Computer science is extremely young. And if you start studying mathematics or if you start studying computer science, you are in the first semester or at school, you're confronted with the heroes of that discipline. And if you study mathematics, you hear about Euclid and these people. If you start studying computer science, you hear about Hoare and about quicksort. And it's so amazing that as a computer scientist, you can be at that meeting and you can meet that person who invented quicksort. This won't ever happen to mathematicians. You really have to time travel to really meet those pioneers. Tony Hoare, he is born by British parents in Ceylon by that time, now Sri Lanka or Sri Lanka as you want to name it. And he went to school in Africa and Ceylon, and then he started his bachelor back in the United Kingdom, and he studied first Greek, Latin, and philosophy. So not even mathematics, but somehow philosophy drew him into logic and into mathematics. And during his military service, he learned Russian, and then he went to Russia as an exchange student or guest student. And in his time in Moscow, as I read it, he invented quicksort by the age of 25 or so. So this should encourage the young researchers. So 25 is just the right age to do milestone seminal work. And so he is the inventor of quicksort, but he did many more things. And one very important thing in his academic career was always correctness of programs and to base programs on axioms. And his seminal work on the axiomatic basis of programming languages also led to, I think, quite some progress in the field and of defined semantics of programming languages and so on. For many of us computer scientists, we all know the Hoare calculus, and another achievement he did is thinking of parallel computation. So he is also the inventor of CSP and many more. So for me, it's a great pleasure to have him here. He got the Turing Award already in 1980, which is a while back, and he even got knighted for his achievements by the Queen, so he's Sir Tony Hoare, and he also got the John von Neumann Medal. He's member of the Royal Academy of Sciences and of Engineering, and so for me it's a great pleasure to introduce to you Tony Hoare here on stage with his presentation on the discrete geometric representation of concurrent program execution.
Well, it's a great pleasure to be here again. I was here last year. I gave a lecture on Euclid, and today I'm continuing the theme of geometry in more direct application to computer programming. I must thank Barbara Liskov for making such a splendid introduction to my talk. I hope that she will agree that what I'm saying is just an example of what she has told us so persuasively in her last talk. Well, I have been interested in the last few years in going back to the roots and the semantics of programming languages, and identified three different ways of approaching, well, I haven't identified, there's a standard three ways of approaching the semantics of programming languages. First one has been called denotational semantics, and I will suggest that for concurrent programming, a foundation in discrete geometry might be the best way of doing a denotational semantics, of relating programming languages to mathematics, and it has a direct application, possibly in the far distant future, if you all work very hard at it, for diagnostic tracing of concurrent programming. Then next, algebraic laws, using the immense power of algebra for simplifying the reasoning and understanding of complex mathematical domains. And this is used directly whenever a compiler optimizes the program for execution, more efficient execution on the available computer. And finally, rules of logic, which are used for reasoning about the properties of programs, in particular their correctness. And my message is that one can prove from a geometry what the algebra that it obeys is, and that from the algebra you can derive a logic, and from the logic you can derive the semantics of a programming language, which has two forms: an operational semantics, which deals with the business of implementation. For each program and for each set of input data, it will give you one execution of the program, and that's the operational semantics due to Plotkin and used by Milner, and the verification semantics, which is attributed to me and recently developed by Peter O'Hearn, that enables you to prove things about all possible implementation, all possible executions of a program. So for a single execution, you use operational semantics in the design of your compiler or your interpreter. For proving correctness, or even only partial correctness of a program, you need a verification reasoning logic, which tells you about every possible execution of the program. So start off with discrete geometry. I'm going to talk about, first of all, a single execution of a program whose actions are recorded in a trace of its execution. And I will draw the actions on a two-dimensional plane. Here we are. In which the vertical axis represents time as an ordered set of instants, and the horizontal axis represents space as a set of locations in memory. This is quite a usual kind of diagram that you get in physics, where time is written as on a pen recorder in one dimension, and the position or other attributes of your experiment are readable in the other direction. Points represent actions performed inside or in the immediate neighborhood of a computer, or when I say computer, I mean a computer system, a network, or even a data center, or even the whole world, all the data centers in the world. And the point lies at the intersection of two orthogonal coordinates, time coordinate, which is vertical, and it represents an object which has been created and manipulated by the program, or an object in the real world, and it has a unique location, the position where the coordinate is drawn, and the actions of the object occur in the same location at different times, obviously. The horizontal coordinate represents a transaction, which is a collection of actions that take place simultaneously. They're on the same horizontal coordinate. but they occur in different locations. The individual actions in a transaction are actually performed by different objects. Now, just in case you think I'm doing real geometry, I shall have to admit there are an awful lot of holes in my argument. The holes are those intersections of coordinates which do not exist as actions. In normal geometry, every intersection of orthogonal coordinates is a point, whereas for me, nearly all the points are empty. Just the same way that most space is empty and most of time is empty of events at any given place. So an arrow is just defined as a pair of points adjacent on the same coordinate. They are neighbours on the line. It's a discrete geometry. There are no points between the intersections of the coordinates. And an arrow represents a dependency, a most important concept in concurrent programming, and indeed in all programming, where the action at the head of the arrow cannot occur before its tail because there is a causal dependency which prevents it from doing so. So no action can occur until all the actions that it depends on have already occurred, or if they're all actions in the same transaction, no action can occur unless all the other actions of the same transaction occur at the same time. I'm going to draw vertical arrows with its head drawn downward, representing the physical fact that effects happen after their causes. On the horizontal arrow, I'm going to draw it left to right, but you should regard that as only a convention. There's no reason why the arrows should not point in either direction, or indeed, as it were, across the room. You can imagine that the two-dimensional plane I'm talking about is wrapped around the surface of a cylinder, and so that even the leftward path for an arrow will bring it around to the right-hand side of the, bring the head around to the other side of the tail. Now, an arrow can have a label attached to it because one of the main reasons that we introduce a causal dependency into our programs is because one action depends on values that have been computed by previous actions. In fact, no action can occur, no calculation can occur until all the values that it needs in the same transaction have occurred before it. So the label gives the value transmitted along the arrow, as it were, from its tail to its head, either by communication. I will draw these communication arrows in a sloping direction, or by storage, because a stored item is conveyed, a stored value is conveyed by the memory from the action which assigned the value to the memory to the action which uses it, or many actions which use it. So here's an example where I have drawn 6 vertical coordinates and 1, 2, 3, 4, 5, 6, 7, 7 horizontal coordinates, and the vertical coordinates stand for objects. The first of them is labeled C query, which stands for an input channel. T stands for a thread. X, which is internal to the box, stands for an integer variable. U stands for another thread. Y stands for another value, another variable, and D, exclamation point, stands for an output port of a channel D. Now, each of these vertical coordinates going from the top to the bottom of the diagram has actions which are indicated by black circles. and the points marked on each line are those performed by the vertical line that it is on within the transaction shown by the red horizontal line which it is also on. So all the vertical lines on this diagram, except the line labelled X, begin outside the box and continue after the end of the box. The X is entirely local to the diagram. The 7 horizontal lines stand for transactions. All the actions of the same transaction take place at the same time, or at least they appear to do so. The 3 transactions on the left represent the execution of the commands of the thread T. The 4 transactions on the right are executions of the thread U. And each horizontal line is labelled by the name of the basic command of the original program whose execution caused this transaction to take place. So let us consider now the rather brief and uninteresting history of the variable x occurring in the middle of the diagram. The first event in the life of this variable is an action by its initial owner t, the thread t, which allocates it by issuing a command like new x. The next action is an assignment action which assigns to the variable x the value 8, which has been read as part of the same transaction by input on the input port of the channel C from the outside on the left. The value 8 was input on the channel C and ends up labeling the vertical line for the variable x. And finally, the thread T releases the variable x so that it is no longer local to the variable T, no longer owned by the thread T, and becomes available for acquisition and use by some other thread. So that's indicated by the third transaction on the left, release x, which gives rise to a communication with some other transaction, communication indicated by a sloping line, still vertical, but sloping for a reason that we'll see shortly. In order to acquire a variable, the thread U issues an acquire command, and from then on the variable is local to the thread U rather than the thread T. And the only thing that the thread U does with it is to output its value on the channel D, having added the value of its local variable y to the channel. So on D, output y plus x. And finally, the thread U disposes of its newly acquired variable x, and that is the last that we shall hear of the variable x. And the same is true of other objects, obviously. The very first action of every object is to be allocated, and the last action is to be disposed. I take that as a nice illustration of the power of algebraic concepts to define rather precisely the meaning of the actions of acquisition, of disposal and allocation of resources. I don't have to tell you how these things are implemented, but you can identify uniquely from looking at the diagram which of the actions were allocation actions and where the given object has been disposed afterwards. So you notice I've been drawing a rectangle around the trace that I've been showing you. and I will call that rectangle a box because it's a shorter word. The contents of a rectangle represent the execution of a single node of the program syntax, a single structured statement in the text of the program itself. For example, the body of a conditional, a then clause, or the else clause, or the body of a method that is called remotely. A rectangle, as you probably know in geometry, is surrounded by 4 edges, and 2 of them are at the top and 2 of them at the bottom. The top edge is a horizontal edge, and it is crossed by the set of the vertical input arrows of the module, which is represented by the box. And we can define what the input arrows are because their head is in the box and their tail is outside the box. Bottom edge is similarly the set of the vertical outputs of the box. And the left and right edges contain the horizontal arrows, input on the left and output on the right. And just for emphasis, I've drawn the box in bold on this slide, but you're now familiar with the picture that's inside the box. And the point about the box is that it crosses the coordinates at certain points, and these are the points at which the inputs and the outputs of the box are made available to the external world. So now I come to the principles of modularity. We can split a box into 2 parts, 2 component boxes, which, following the practice of geometers, I'm allowed to give them names, P and Q, and they're split by an edge which they share. There are 2 ways of drawing such an edge. One of them is vertically, to introduce a new vertical edge, or horizontally. And on the next slide, the edge will be horizontal. Horizontal edge represents the state of the memory when the first component of the composition P ends and the component Q begins. It contains only vertical arrows. These vertical arrows are the memory locations at which the variables are stored, and Q can read the values and operate on these same variables that have been produced and assigned by P before Q starts. And I'm going to economize on concepts by defining an edge as the set of arrows which cross it. An edge acts as an interface between the box and its external environment, as Barbara has explained, and an edge tends to be orthogonal to the arrows and the lines, the coordinates which cross it. So here's a vertical example of a horizontal edge introduced into our familiar diagram. I've left out all the labels because they're now irrelevant for our purposes. You notice that the vertical line inherits all the objects which have been produced by P and passes them on to the component Q. The interesting thing is the diagonal line in the middle of this diagram, where the ownership of the variable x is transmitted from the left to the right. A vertical edge, we can draw a vertical edge passing through the same diagonal, and it separates the concurrent actions of the thread on the left, P, and the thread on the right, Q. The so I think now what we can do once, we can do twice, and the splitting can continue. If the first split was horizontal, we can then make a vertical split of either or both of the components into yet smaller components, producing a sort of hierarchical structure which is recorded in a continuous text, by a mathematical text, by using brackets to indicate the order in which the splits are made. So the title of this slide, with a semicolon in it, indicates the sequential composition denoted by the horizontal line, and the two vertical lines in the text at the top of the slide indicate the concurrent composition of the two operands which stand on either side of it, PQ and P dashed Q dashed. And here is the a picture of the of what happens when the first split is vertical and the two second splits are horizontal. Well, the process of splitting the boxes by drawing a line from the edges of the box, a new line which is shared between the two components, can continue indefinitely. Notice that each arrow in the diagram is only split once by an edge that is drawn later. So even at the end of the process, we can identify exactly which edge splits each arrow. So in the end, the process will stop when every arrow has been split, because then there's nothing more to do. I call this process quadrangulation because it's similar to the geometric process of triangulation, which is widely used to compute the areas of figures in geometry. So now let's see, could you tell me how much time I have left? 15? Thank you. The algebraic laws are, of course, laws which hold between programs, between those little texts containing sequential and concurrent composition. As you all know, algebra its purpose and task is to translate a mathematical text, a term or an expression, from one form to another which is better suited for a different purpose. And it's used to translate them back again if that's what you want. And I will write my translation rules as orderings, P below Q, where P is more suited for one purpose, for example efficiency, and Q for another, for example clarity or abstraction or realism. And the point of a translation rule when applied to a program is to justify the optimization, allowing the implementation to replace a program which has been written like the right-hand side by an implementation that behaves like the left-hand side. The algebra itself doesn't guarantee that this is going to give you greater efficiency. In fact, it doesn't even guarantee that the left-hand side is defined. But nevertheless, we've separated our concerns on the validity of the optimization, or the validity of the transformation, from the concern of whether the result is going to be more efficient, which is an incredibly important, obviously, property, but it's implementation dependent, and I have chosen to neglect the actual application of my optimization rules, leaving that to the language designers and implementers. And equivalence is defined in the usual way as the conjunction of an ordering with its converse. And it means that for all relevant purposes, the two sides of the equivalence are equal, they are intersubstitutable. So I'm going to introduce an order algebra in which the equality symbol of the algebra is replaced by an inequational ordering because that's what I want to do. Thank you. The ordering relation has to be a pre-order in the sense that it is transitive. Transitivity is defined by the proof rule on this slide, and reflexive. And the other important point about the order used in order algebra is that it is a precongruence, and this requires that all the operators of the algebra are monotonic. That if you reduce any component of your program, and if you transform any component of the program, then you transform the whole program in the same direction. And this property of monotonicity is absolutely characteristic of all programs and all operators that are put into the programs, because they support the engineering principle of stepwise design and top-down design method, where you can design the most abstract program first, and then at any point replace any part of the design by a further, more detailed design which implements it. So that is why the monotonicity is so important in programming and in other engineering disciplines. Now, the algebra that I'm going to introduce to you is called concurrent Kleene algebra, because it's very similar to the Kleene algebra that's familiar from automata theory. The two operators that I've introduced are associative, and they have the same unit. The unit 1 is an empty box containing no action, and if you have no action, a null command, it's going to have no action whether it is performed in parallel or sequentially with some other command. So obviously true, isn't it? I'll prove it again, but I'll prove it shortly. Then there's a vital law which is called an interchange law, and it permits the concurrent composition, which is on the right-hand side of the inequation, single bold bar, can be implemented by the semicolon, which is the major connective on the left-hand side of the ordering. As a result, the two semicolons on the right-hand side of the inequation are implemented by the single semicolon on the left-hand side. And the idea is that when you run them in parallel, the decision as to how to time the various actions of the two components is left to a scheduler, left to the implementation. And the implementation scheduler, maybe at runtime or even at compile time, is allowed to choose to execute the two semicolons on the right-hand side at the same time as the single semicolon on the left-hand side, thereby synchronizing the two threads on either side at the point at which they both reach their respective semicolons on the right-hand side. And the theorem, I'm going to prove the first theorem now, that a sequential composition of P and P dashed is an implementation of the parallel composition of P and P dashed. And that is proved from the interchange law by replacing two of the variables by the unit 1 and then cancelling the unit 1. So if you replace Q and Q dashed in the interchange law by 1, you can derive one of these commands, and if you interchange P and P dashed, no, the other two, you could derive the right-hand one. Notice that this pair of laws justifies implementing the concurrent combination by an interleaving, or just by an ordering in this case, of P then P dashed, or P dash then P. So that's a characteristic that the implementation has a choice as to which one of those to execute the concurrent composition by. It's a very important principle of concurrency because it enables in implementation to run a program that you've written with lots of concurrency, many threads, on a configuration of processors which have very many fewer threads. So the interchange law actually tells you that you can run a multi-threaded program on an actual physical configuration that does not have enough processors to exploit all the parallelism in your program. I have to define now, relate this to the geometry by defining the ordering of the boxes. And if R and S are boxes, then I define their ordering. R and S have the same points and the same arrows and the same labels, but maybe different quadrangulations. Only the quadrangulation changes. And it changes in the way that some of the vertical edges of R may be changed into horizontal edges of S. If you remember, in the first part of my talk, I showed how the diagonal arrow in the middle of the diagram started off as a vertical, as crossing a vertical edge, and on the second diagram it crossed a horizontal edge, or the other way around. I'm afraid I don't always distinguish horizontal from vertical in an accurate way. So more arrows in R may cross a horizontal boundary in R than in S, because in S some of them have been turned to cross a vertical boundary instead. And as a consequence, in fact equivalently, more arrows may cross a vertical bar in S than in R, and informally we say that R is the interleaved version, the side R, is more sequential than S, and S is more concurrent than R. So here's a pictorial representation of the theorem that we've proved already, and a pictorial proof says that every vertical edge on the left-hand side is either wholly inside P or wholly inside Q. That's a property of the quadrangulation process. No two edges ever cross. And the same is true on the right-hand side. And therefore, there are every vertical edge, at least, remains vertical on both sides. Every edge which is vertical on one side remains vertical on the other side. All the edges that pass from P to Q will be vertical on the left-hand side because they cross that horizontal split in the middle, and they'll all turn into the other kind of edge. They'll all cross the vertical edge on the right-hand side. So the proof. that 1 is the unit is also very simple. There are no points in 1, and therefore there are no crossings of any edges between 1 and p, or anywhere else. And therefore the only things left are the points and the edges of p. The two quadrangulations are the same. Equivalent. Associativity of semicolon and of parallel is proved in almost exactly the same way. But of course it would be easier in an elementary class to say that when you draw them they look the same. Now, commutativity of the parallel combinator cannot be proved from this principle, and would have to be introduced later if you wanted it. But maybe you don't want it, and for some purposes it's best not to have it. So finally we have to prove precongruence, the monotonicity of the ordering relation, which states is also fairly obvious if you consider the geometrical interpretation. And here is the interchange law. I won't draw a picture this time, but I'll just reason informally. On the left-hand side of the ordering, the arrows that cross a vertical bar are either from P to Q or vice versa, or they're between P dashed and Q dashed. They cross the vertical bar which separates P from Q or P dashed from Q dashed. Now, every one of those arrows also crosses the vertical bar on the right-hand side. If you enumerate them, you can see on the right-hand side there's a P on the left of the vertical bar and a Q on the right. So all arrows going from P to Q on the left go across a vertical bar on the right, and the same similarly with P dashed and Q dashed. Final point I want to make is that interchange permits interleaving. I've been too enthusiastic to end. Have I? Here's a proof. No, here is, oh no, I can miss that. Let's have a look at an interleaving example. I'm going to interleave two sequential compositions. One of them contains the letters A, B, C, D, and the other one's X, Y, Z, W, and I'll write them without the semicolons because of it doesn't matter by associativity. And I'm going to show that the interchange law permits the proof of any interleaving of the concurrent composition shown at the top of this slide. By applying associativity at each step, we choose where we want the dividing semicolon to be on the red side and the black side, and apply the interchange law, getting the third line. Then we can use associativity again to place two semicolons, two more semicolons in the expression, and apply the interchange law again, implicitly appealing to monotonicity at this point. And then finally, after an amazing number of more steps, we get to the final conclusion that the interleaved string, in which you can see from the colouring that the ordering of the original semicolons has been left unchanged. So my summary, and I've really only dealt with the bottom step of this, that on discrete geometry we can prove the algebraic laws of concurrent cleaning algebra. From the algebraic laws we can prove the logical rules written in the form of proof rules, which are used by the operational semantics of Plotkin and Milner and the verification logic of Hoare and O'Hearn. Thank you very much.
Yes. Thank you very much. There's time for quick questions. Here is one in the back.
My name is Theodor Schlickmann, European Commission. I have a question to one of the definitions you brought in the beginning. There was a definition of a point, and one phrase in this definition says outside a computer or close to a computer. And I wonder what do you mean by that? And I also did not see any reference to this definition later on in your presentation. Thank you.
Thank you. The exact interpretation of what the actions means has to be left informal and should not be used in any mathematical proof using the abstract axioms of your mathematical system. When you apply physics to the real world, there is obviously should be a very close connection between your formulae and what is happening in the physical world. But that connection can only be described informally by saying X stands for the position of this pulley in this assembly, and Y stands for the velocity of this. And so I think the first, your first point is a very valid one, but it's outside the scope of my talk, and possibly even of the whole of mathematics, to describe its own application to reality. I'm using the words actions, and actions occurring inside a computer and outside a computer, purely in this informal sense of saying what things stand for, rather than in any sense defining what they mean in any mathematical sense.
One last question, maybe.
Do you think it would be worthwhile to modify a spreadsheet program so that it could accommodate your notation and your rules? And of course, we'd have to have diagonal arrows added to the spreadsheet.
I don't know whether spreadsheets draw nice straight and diagonal lines, but I would be very pleased if anybody here or anybody else were to make a graphical illustration of what I've been talking about, which could at least illustrate my lectures, and I think lead to an inspiration of a more sophisticated graphical scheme, which would aid in program testing and program debugging. Because if you are debugging a program, I imagine that you might be looking at a screen, maybe something even like a sat-nav screen, which would take you along any road you wanted to go, and the roads that you want to go are the lines, the causal chains of actions which lead to detected errors, and actions and the lines which enable you to travel at a speed of your choice to the places where a detected error might reveal itself as something more serious. So there are systems which are used in debugging relaxed memory programs. A colleague of mine Jade Algarve has written one called Herd, which follows the causal relationships between events and enables and there are automatic tools which generate events that are counterexamples to a conjecture which is put forward by the engineer. These have proved extremely useful in discussing the design of relaxed memories.
Thank you. So we are far behind schedule now, so please excuse if you have more questions, maybe you take it to the break, and all the volunteers who want to illustrate that graphically, contact Tony Hoare on the break. Let's thank again Barbara Liskov and Tony Hoare for this wonderful session.
Thank you. Thank you.